Yeah, but we're not to phasing lines yet.
Yeah.
Actually, we don't get to phasing lines. That's the extra. Okay. Directional antennas. They have gain, which is defined as a relative increase in power radiated in the direction the antenna is pointing. There's actually no power gain per se. If you've got 100 watts going into the antenna, it doesn't matter what your radiation pattern is, there's only 100 watts going out. Now, when you concentrate it, you get more watts per square meter. It's still 100 watts in, 100 watts out, or less, depending on several factors.
I don't know about 100% efficiency in the feed line and
Right. But we're talking theoretically. Perfect world, zero loss on your coax, all that. We specify that gain in dBs, and we make it either relative to the isotropic antenna, which you should have heard of before, which is a theoretical point source antenna, which would have a hemispherical radiation pattern. Or we use it relative to a dipole. We represent that by dBd. And the difference is a dBd is 2.15 dBis. So a dipole has about 2 dB gain more than the theoretical point source antenna. We also,
right direction.
well, in its broadside radiation pattern. We also talk about front to back ratio when we talk about directional antennas. So they'll have higher gain in the forward direction or front direction than they do in the back direction. And in case of Yagis and I guess log periodics, that can be up close to 20 dB relative difference between the forward and the back. The bandwidth is going to be narrower than if it was like a straight dipole or vertical. You don't get something for nothing. If you concentrate the beam, then you get more power in that direction, but you get a much narrower bandwidth. And they're saying it's probably 2 to 3% of the center frequency for like a Yagi or a log periodic. You can get some of the bandwidth back by using larger diameter elements. Good morning, Ernie. How are you today? Oh, that's good. There's coffee. You any insights on directional antennas? Do you have any insights on directional antennas?
They're good.
They're good.
And they're quieter than rifles.
Okay. What about the bandwidth?
They're narrow.
You've read the chart. What about the size of the elements?
But same as no balloon.
Well, you're supposed to say it's wider bandwidth. I don't know that it affects it that much, but theoretically it's supposed to. How does antenna gain stated in dBi compare to gain stated in dBd for the same antenna?
Yeah.
Close.
1.5 dB.
Yeah.
Maybe not here. Yeah.
Well, when you yeah, if you specify the gain of your antenna in dBi, you get a bigger number, which is why they tend to do that.
The spirit was from the same video. Came down on the rating right away.
I saw one the other day. We could figure it was DB MIG, and it was for some weird um, magnetic loop, except it was a cylinder. Looked like it was about a foot high, maybe a couple inches diameter. I forgot the name of it, but it was a weird thing. And supposedly they did some comparison, and it had about the same gain as a bigger regular size loop. Yes, and very, very narrow, very, very narrow bandwidth.
No, because we've got two circuits basically. Two circuits. So the voltages inside are extremely high. But the capacitor, you're usually a vacuum capacitor. They run with 300 hours. Like the simple. That's why you'll see a lot of those are saving only.
Yeah. And even those are not cheap.
75, $300.
Okay, front to back ratio is the power radiated in the major lobe relative to power radiated in the opposite direction. And normally we refer to the major lobe as the front lobe. And that's normally where the direction the antenna is pointing in. And that front to back ratio can be up to 20 dB. And the major lobe is the maximum radiated field. And you see here in this example, it's very narrow. There are some, typically you'll get a couple little side lobes. And if you like with the Yagi, if you play with it, the number of rectors that you put on it, the boom length, the spacing, and all those things will affect that front to back ratio, the gain, how many little side lobes you get. So that's a whole different, probably spend a lifetime playing with those kind of things.
And because have all that obnoxious noise out the backside.
Yes. What does the front to back ratio mean in reference to a Yagi antenna? Well, I know, but you're supposed to know the answer. Power radiated at the major radiation lobe compared to that in the opposite direction. What is meant by the main lobe of a directive antenna? Viewers? Are you referring to the scotch or the container for cryogenic?
Well, I'm more a
Oh,
but I call this concept skill too.
the direction of maximum radiated field strength from the antenna. None of these. Vertical angle radiation. Point of maximum current and radiating an element. No, wouldn't have anything to do with it. Standing wave point. Okay, Yagis. It's a multi-element directional antenna, basically composed of half-wave dipoles that are shortened, in the case of the reflector, lengthened. The feed point, which we call the driven element, is typically a quarter wave dipole. In some of the formulas, it's slightly less than a quarter wave. On here, it's showing 0.44, and the reflector behind it is a half wavelength. And that's spaced such that when it reflects the wave from the driven element, it's 180 degrees out of phase. So it's spaced such that that reflected wave adds to the wave coming out of the driven element. And then you have in front of it, you have directors, and each of those gets slightly shorter, and the spacing becomes, I guess, sort of exponential. But like I said before, these things can all be adjusted to affect the front to back gain ratio, the gain of the absolute front gain of the antenna, and also affect the bandwidth a little bit. Plus the size of them will affect the bandwidth. They have a very narrow bandwidth, a couple percent around the center frequency. However, it's still wider than a magnetic loop. You don't have to retune this. I guess in most cases, can you get an entire band with the Aggie?
Get what?
The entire band with the Aggie?
It will come in whole band, but it'll be like 3-to-1, but set it right in the middle. We had a real nice, depending on the band also.
Right.
We had a real nice 20-meter beam years ago. A ribbon element was motorized. We could run the cannonballs. Yeah. It was great. We didn't get out very much. It's freaking cool. We usually hold it down.
Oh, yeah. What is the approximate length of the driven element of a Yagi antenna? Approximate. Half a wavelength or slightly less.
It's proven going forward.
Depends on how it's fit. Okay, what is it? In a gamma match, it's a half wavelength. There's no separation of elements. I know that because I read it.
It was never wrong, right?
And it's coming up on a chart soon.
Oh,
How do the lengths of a 3-element Yagi reflector and director compare to that of the driven element? Right.
yeah.
Reflector is a little bit longer, and the directors keep getting shorter and shorter and further spacing.
About 1%. You're insane. And they're going to
Yeah, for moon bounce, you're looking at about 20 elements. 4 of them in an array,
Yeah.
and a preamplifier, and 1500 watts. Then you might hear an echo. Because a friend in the NASA club does that. Huh?
So,
Um, yeah, you made me forget his name. Scott. He doesn't do it often, but he went through all the trouble to do it and said, on single sideband, you say, hello. Oh, you just barely hear it coming back. And you spend a whole lot of money to do that.
same thing. The things that made this tightly locked, we always keep it same side.
Right.
Affiliation form of amateur organizations.
Well, there you go. A repeater.
No, that's.
Well, there's enough solar. You could power a repeater.
Yeah. We can go back to the old Pecco subway.
Okay. A Yagi Uda. The Yagi, and we normally kind of refer to it as a Yagi. It's technically a Yagi Uda. It should really be an Uda Yagi. It turned out that Dr. Uda did most of the development, but he worked for Dr. Yagi, who took most of the credit. So you can change the characteristics of it by increasing the boom length and adding more directors, which gives you more gain. Using larger diameter elements to increase the bandwidth. Changing the boom length and the separation of the reflect or the directors, the spacing of them, how many of them will all affect the front to back ratio and the total gain. So you can, and there's a lot of online calculators for doing a Yagi where you put in the numbers. It'll tell you, if you want X amount of gain, it tells you got to have a boom of this long, you got to have this many directors, and each one has to be spaced so far. You can kind of customize one if you're building it yourself. So what is the primary effect of increasing boom length and adding directors to a Yagi antenna? Increasing length and adding directors.
Like that.
Right. Which of the following would increase the bandwidth of a Yagi antenna? Larger elements. Which of the following can be adjusted to optimize forward gain, front to back ratio, and SWR bandwidth of a Yagi antenna? Right. Because all those, things affect the impedance of it. So it's going to affect your SWR in addition to trying to get the gain and front to back ratio. So if you want to set it up for 50 ohms, I don't think that's a normal Yagi, but assume if you wanted 50, then you'd have to go play with your boom length and the spacing and stuff in order to maintain the 50 ohms and try to optimize the gain. Oh yeah. There's calculators for everything online.
People don't build their own.
Yeah. Well, unless you're doing it at VHF or UHF, and then it's not bad for fairly small elements. Improvements on the Yagi Uda. If you can stack them, if they're horizontal, you separate them by half a wavelength and you get a 3 dB gain. So you've got two antennas that are far enough apart, they're not supposedly interacting. So you get twice the gain. It also narrows the lobe, so you get a lower angle of radiation, or lower takeoff angle. If you're wanting to do something with vertical polarization, you can do them vertically, and they still have to be separated by half a wavelength. But you just turn that whole array sidewise. And then you can put 4 of them up in an array. There you got to have, I guess, a phasing cable, but you can get 6 dB at 4 times the cost.
What's the one? What's the max?
Oh, that great big wall thing?
One that has about 500 elements on it, or,
Yeah, the really big thing, the old,
yeah,
it was some kind of radar, wasn't it?
it was used as a radar.
No,
One, sure.
yeah.
Yeah,
I think Steve had some pictures of that at one of the meetings, right?
yeah,
It showed some people, standing up on a thing on top of it.
it was a massive radar. No, I'm smack, then wiped out radios all on the 20 feet and 20 meters. You could hear it on short. Well, they also have the new satellite information. They bought like 500 tiny dipoles.
Oh, yeah.
Yeah.
One of the Russian radars I worked on, they called flap lid, and it was about an 8 foot diameter plate that you could tilt and rotate, and it had 1,024 little dipoles on it. So it was a uh, directed beam. You just change the phase, and you could move the beam anywhere you wanted.
Same thing with radars.
Well, this was radar.
The phase arrays change, on one ship. Around, all the way around. All the elements are driven slightly out of phase, so that when one direction go around and also up and down, so that the directional distance and everything. I found that those are the greatest until now that find burns when you were looking for fishing locations on the.
Okay, in free space, how does the gain of two 3 element horizontally polarized Yagi antennas spaced vertically 1/2 wavelength apart typically compare to the gain of a single 3 element Yagi? 3 dB higher,
Doubles it.
doubles it. What is an advantage of vertical stacking of horizontally polarized Yagi antennas? Besides gain.
It narrows the elevation.
All right, narrows the main lobe.
And also, tell what's trying to pick off angle.
Uh, well, that's part of lowering the lobe
Yeah, okay,
because the takeoff angle is going to be the maximum, the peak of that lobe.
right.
So if you lower the lobe, takeoff angle lowers too. Right?
Good.
Okay, impedance. It's normally less than 50 ohms. I don't know what it normally is. I don't have one yet. Think about building one for 70 centimeters. There's two typical ways to feed it. One is with a gamma match. The other is a beta match, or also called a hairpin match. The case of the gamma match, it's called a gamma because the configuration looks like the Greek symbol gamma. I believe them. I don't remember what gamma looks like. Anyway, you have a uh, sliding conductor that you move along the driven element to find. It's kind of like when you're feeding an off-center dipole. You're trying to find the impedance point that you want to feed it at. And the other part of this has a tube connected to it. And inside of it is in a lot of cases, it's a piece of coax center with its dielectric without the shield. And this tube, you also slide back and forth. So this is essentially a capacitor. So you can change the capacitance on this feed as well as the point where it's feeding the driven element to not only match the impedance you want, but kind of cancel out the inductive reactance with that capacitor. At least that's how I understand it works. And you can get pretty close to 50 ohms that way. So you don't need another matching transformer or anything. The hairpin match is a shorted loop. So it can be a piece of transmission line shorted on one end, and its length will determine what the impedance, what transform ratio it has. If you have a quarter wave piece of transmission line and you short one end of it, the opposite end is going to be infinite ohms, or it's 0 ohms on one end. So that's how the quarter wave transformer works. And any point along there is going to be some impedance between 0 and infinity, many thousand ohms in the real world. So that's how you adjust that to get the impedance match. And that's all you need to know for the general class about a beta. You don't have to calculate it, fortunately. You can also get 50 ohms that way. The other difference in a gamma match, the driven element can be continuous half wave, and it can be attached to the boom along with all of the other, the reflector and all the driven elements. And normally, like in the beta match, it's got to be isolated from the boom and the other elements. So that is one advantage of the gamma match.
I think most ones I've seen ever gamma match.
And hopefully you only have to do this thing tuning one time. So which of the following is a characteristic of using a gamma match with a Yagi antenna?
There you go now.
What is a beta or hairpin match? Yeah, I think we have a lot of alphas here. Okay, let's see here.